Right, welcome to the GLHMM GUI tutorial. In this video we'll walk through setting up and using the GLHMM GUI app, which is based on a Streamlit interface. So GLHMM stands for the Gaussian Linear Hidden Markov Models, which is an open source Python library with a focus on neuroscience. So normally we call Hidden Markov Models for HMMs. So it lets you fit different types of HMMs to brain signals like EEG, MEG, fMRI, or other recordings that you measured over time. And then it helps you to uncover hidden states in brain activity. We can then test how these states are associated to different behavioral measurements that we got from the people that we have recorded. So that could be age, sex, IQ, or some other simultaneous recorded signal like pupillometry, heart rate, and skin conductance. So the Streamlit GUI app was made to make these analysis more accessible. So instead of writing Python code and scripts on your own, then you're supposed to have this friendly user interface where you can upload your data, run the analysis, apply the statistical test, and visualize the results. So it's especially handy for neuroscientists or data analysts who want to try out the GLHMM without delving into programming. So we assume that you have already Python installed on your computer for this tutorial, but everything else we will set up and show from scratch. And the GUI follows the pipeline that comes from this paper here, a comprehensive framework for statistical testing of brain dynamics, and is located in my local GitHub repository. And we have to go down to the GUI version here. Okay, and I'm using a Windows computer, by the way. So the first thing we have to do is we have to clone the protocol. All right, and I got a folder called GitHub and essentially I will just copy this line here and clone it to this specific folder. And it's quite common when you're working with Python that you're creating individual environments that can handle different packages that you're installing, so you don't have any conflicts. So we will do that by copying this line here. So we are creating a new Python environment and we call it GLHMM GUI with a Python version of 3.10. So I already got this one, I forgot to remove it, but now we're gonna override it. Right, so now we have created this Python environment, and then we have to activate it, and we can actually just see what we're supposed to write here. So conda is essentially also what I wrote here. The third step is conda activate the GLHMM GUI. And you can see it's activated when you see this part here of the code. So this is a new environment, and what we have to do is we have to install both packages, the GLHMM and Streamlit, which is where the GUI is visualized. So we're gonna install the GLHMM first. And now we have to install Streamlit. Okay, both packages has been installed. We can now navigate to the GUI directory and run the app. And we essentially just copy this line, we'll copy both essentially. So you can see we have navigated to the GitHub page, the GitHub repository, and then the folder GUI. And now we have to run this line here, Streamlit run, and then the file. And from here, the GUI will essentially open. Yeah, it will take some time. You can see my head is actually blocking the process that we're initializing the app. Right. So now we are in the introduction page of the GLHMM. And the first thing we have to do is load our data. So that is the brain data that we have recorded from these people, right? And in this example here, I'm using a subset from the HTTP dataset, so the Human Cognitum project, where we have just randomly selected 100 people. Yes, and then we'll load the data. As you can see, this drag and drop function here, it got a limit of 200 megabytes, which is quite small. And essentially, when you're working with larger data, then it's quite common that more than 200 megabytes, right? So essentially, you essentially just have to copy the directory where the file is located in, and then I can add the file name, and essentially it gives the same thing. So that is just because the drag and drop function doesn't work. But then if you just write the correct path to a direct path to a folder or to the file, then you can load it directly as well. And if you got multiple files that you want to load from a folder, then you can also define the folder path as well and the folder names, the file names. All right, but now our brain data is already loaded, and then we have to do the statistical test, right, on some behavioral measurements, like I said before. Could be age, sex, IQ, language ability, memory ability. So in this case here, we are loading this file that I've prepared. Now the behavioral data is loaded successfully. And this is the shape of our data. So in this case, I actually got a 3D shape, so number of time points, number of subjects, I got 100 subjects, and then I got 50 brain parcellations. And in order to use the GLHMM, we actually need to reshape this 3D matrix into a 2D. And by that, we have to define, okay, is it actually time points we got here, or is it the number of session or people and features? And in this case, it is. So I have to reorder in this format. And you see it's been shaped to 480,000. All right. And for the HMM to work properly, you have to define the number of time points that belong to each subject. You saw before that there was 4,800 time points, but this is just a demo here just to illustrate how it works. So for instance, you have to say, okay, from time point 0 to time point 5,000, that belongs to subject or session 1, 5,000 to 10,000, subject session 2, and so forth. So we can either load a file that got this structure, or we can just manually generate these indices. So let's see. We know we got 100 subjects, but let's just write some random number. So as you can see, it gives an error because within 100 subjects times the number of time points, it does not correspond to the length of your data. So we just correct it, and now we can see the indices has been created. So you can see for each session or each subject, you can say that time points 0 to 4,500 belongs to that person, and then it goes up to the end. And these are the behavioral data. In this case, we got age in front, and then we got some other measurements. Good. And like I said earlier, we are following the paper from this paper here, A Comprehensive Framework of Statistical Testing of Brain Dynamics. And this is the pipeline essentially. You got your D matrix and your R matrix. So that is what we have just loaded here. So that is the brain data. And what we have to do is we need to run a HMM on this brain data. And then we're gonna test the association between these hidden states that we are decoding from the brain signal to these behavioral measurements. And from there, we can apply different statistical tests. The framework is using different methods, is mainly using permutation testing, but there's also Monte Carlo resampling. And from there, we can choose if we want to do a multivariate test, a univariate test, or CCA, chronological correlation analysis, or some other tests as well. These are all fully documented in the paper, so we're not going depth into it here. And then you can also visualize the results. So you can see, for instance, here you got some epoch signal where you can say, oh, at this, yeah, so in this example here, you can, for instance, see that you got two conditions. If a person seeing an animate versus inanimate object, and then you can calculate the differences here, then you can use these statistical tests to see where we actually got significant difference between these two conditions. And that can be done in a multivariate test where you look at all state time courses together, or you can do a univariate test where you look at one state at a time in relation to these behavioral measurements. Or we can just do what I'm planning to do here, where we have these HMMs, and then we can try to see how they are relating to different behavioral variables like sex and age. But now we got 10 features in this case, but the same setup. All right, now we go back here. So now we have loaded the data. Then we have to go to the pre-process stage, and that is all about preparing the data for modeling. So in many cases, especially with time series data, we need to standardize or normalize the signal for each channel subject so it's comparable. So this is normally done by subtracting the means and dividing by a standard deviation of each time series. So you got a mean of 0 and then with 1 unit variance. And you can see in the pre-processing steps, we got many checkboxes. So you can, for instance, define your sampling frequency, or you can downsample it, and we got some helpers that can actually help give some further explanation of what each function is doing. We can filter our data, so we do a band pass, high pass, low pass. Just set it to none. Different transformation, detrend it, extract the Hilbert transformation, where we can extract the power or the phase, embed the options. So these embedding options, they are required if you want to use different types of HMMs. So by default, it will be the Gaussian HMM, but if you're, for instance, is enabling some lags, then you will use a HMM TDE. It's already described in these papers here. And if you want to use a HMM MAR, then you have to define autoregressive order. But we're not gonna do that. We are just gonna standardize it. And then we will also save the results. So we just do the pre-processing. All right, that's done. From here, we can then set up the HMM parameters and executing the model fittings. So on this model page section, you can control the variety of HMMs that you want to apply, and it includes the different or typical options for an HMM. So for instance, you saw in the pre-proc that we could apply the embeddings here, but if you forgot that and you just applied the normal pre-processing, you can also just do the embeddings right after. So for the HMMR, you can apply the autoaggressive order, HMMTD, apply the lags. And then you do that part before running the HMM. So yeah, these are some basic configurations, and they're all part of the paper here, the original paper from Imaging Neuroscience. So the Gaussian linear hidden Markov model, a Python package. So not going depth into this, but what we are doing is we are selecting our preproc data and indices preproc, and then we confirm the selection. And then we can train a Gaussian HMM because that is what we have chosen. And then the HMM will start training. So the thing is, with when you're using Streamlit, you cannot see the outputs that is printed or produced from your Python code, but they will actually appear on the terminal here. So now I'll just let it run. All right, the training now is now complete, and we can now inspect the model. So for instance, we can plot the initial state probabilities. So it shows which state that is highest probability to start for each subject. We can show the state means. Oh, so in this case we didn't train, so it's trained without the state means, so we cannot plot these, but we can plot the covariance matrices for each state, And you can see we got different options here. We can increase the width. Yeah, so that one doesn't look nice. We can decrease the number of columns. We can also plot the transition matrix. So it shows the transition probabilities without the sales transition from one state to another. So you can see there's a high probability from state 3 to state 2. Yeah, so these are some basic plots to expect the HMM model. But now, because we're gonna do the statistical analysis, we actually need to configure our data. So right now we got all these gamma values per time point right, but we need to get some summary statistics if we're gonna calculate the differences between subjects. So we're looking at the gamma values. We're gonna select those. So you can see this has the same amount of time points per subject. And now, because we have only selected 5 states times 5, and then we configure the data. And from here we can calculate something called the fractional occupancy, for instance, and that shows the proportion of time a person or session in this case, or well, it is actually subjects because we got 100 subjects, but it's also the same as 100 sessions, different sessions, and you can see for subject 1, there's a high proportion between state 1 and state 5, for instance, compared to other states. All right, now we can do the statistical test. So we can do a cross-subject test across trials, which is all written in the original paper. So in this case, we cannot do across trials, for instance, because we haven't epoch the data. The same for cross sessions and across state visits. You actually need something called the Viterbi path and not the gamma values. So if you do the across subjects, then we will select the fractional occupancies and then the behavioral data. So you can see we got 100 sessions or 100 subjects, and for each subject we got these corresponding behavioral measurements like age, memory scores, language scores, and so forth, different cognitive scores. And we can do different tests here, methods. So we can do a multivariate test or univariate test, CCA. So let's just do the multivariate test in this case. We run the statistical test, and you can see how it's run in the background. Okay, and we can apply some multiple testing correction. And we just use so you can choose different options here. So you can use traditional ones. So it includes Bonferroni, Benjamin Hotberg, two-stage Benjamin Hotberg, Hummel. So we just choose Benjamin Hotberg in this case. We apply the correction. Then we can visualize the results. So this is the uncorrected p-values, and we can visualize the significant threshold. So for instance, if we set it to 1, then this one will update, and then none of these are above 0.1. So if 0.5, then you can see it here. We can change the title, test. Okay, that I need to update. That will be updated shortly after this demonstration. But you can also change the labels here. So let's say the first one is age. Yes, so now you can see we change the labels here. We can change the wavelength, and we can align the p-values along the height, or say no, then they will untick it, then they will move according to the height of these bar plots. And we can also plot the permutation distribution for each feature. All right, that's it for the first data set that we have here, where we're doing the cross subject test from the HTTP dataset. We can also start over and then clear the whole memory by press clear cache. And from here, we're gonna use some data that is actually part of the original paper. So we're gonna, in this case, we're gonna load the gamma values directly. So these are not, they have already been processed using the HMM. Gonna load this here. And this is actually a cross trial test. So we got measurements that is measured along 15 different sessions. And for each session, a subject is watching either animate versus inanimate object, and then it's done for multiple trials. In this case, I got the indices loaded. All right, so you can see this is the brain data, the gamma values, right? Got these number of time points, and we got 5 states. And for each session, then you can see these are the number of time points that belongs to session 1, session 2, to session 15. And then we got these behavioral data, which is a list of 15. So we got values of 0 and 1. So that is just a stimuli to say, okay, that is for each trial. So for inanimate object, it is 0, animate object is 1. And then it just got the length for each trial. All right. So we cannot do any pre-processing because we're using the gamma values. We will not fit an HMM, and we don't have any model to configure. Yeah. So we actually have to configure we had to epoch the data, right? So in this case, we can reconstruct into epochs. And from here, we actually have to include a file which is called event markers, and that shows for each session it marks the time point where a trial starts. So this start time, condition, and event code. So we can just load this file here, event markers. We'll load these event markers, and we can configure the data. Oh, something happened here. Good. So we had the sampling frequency of 1000 actually, but it has been downsampled to 250. So it's just because of these event markers, they correspond to sampling frequency 1000, but actually these gamma values or the data that I've analyzed has been downsampled to 250. So it had to correspond to the same thing. And with a sampling frequency of 250, then I've chosen an epoch window of 250 as well. So that means a 1 second interval for each epoch. All right. And because we did not use any aggregate measures, we cannot do the cross-trial subject test, but we do the cross-trial test. And you can see we got 250 time points, so that corresponds to 1 second. And this is the number of trials that are being performed, and this is the data and the indices. And we can apply, let's do a univariate test in this example here. Yeah, just to make it a bit faster, let's say 1000 samples or permutations. So this give us a smallest p-value possible, that is 0.001. So this is just a quick and fast way for testing demonstrations. It is recommended it should be 10,000 or more permutation when you do the test. So it gives a p-value of minimum 0.0001. So that's for better detection and also show a more reliable effect if you got more permutations. But because this is just a demonstration, we just choose 1000 permutations or samples. We run the statistical test. Okay, so now the statistical testing is completed, and we can now plot the univariate statistics. So for univariate test, right, we are looking at each state in relation to these stimuli, if there's animate versus inanimate objects. And then you will see along the time points where it should belong. So we can update the X label. So for instance, the Y-axis here could be states. And we can also manually tick. So for instance, we can define the the X minimum or X max for this time point. You can define a number of ticks. So you want to update instead of time points, you could probably change it right to milliseconds. And we can also plot the line plots for each of these. So for instance, we can look at the state 1. So that was we had before. So that is state 1, state 2, state 3. Yes, and we do not plot the null sample distribution when we use a univariate test. Yeah, all right. We have reached the end of our tutorial. By now you should have learned how to set up the GLHMM Streamlit app and know the basic idea of how it works. For further help and information, you should look at the different GitHub repositories or look at the papers as well. Yeah, so I would say thank you for joining me for this walkthrough. I hope you found it very helpful or useful, and you should now be confident at setting up the GLHMM Streamlit GUI on your own. Okay. Bye.